So, we are situated here in room 72 in the middle of the World Languages Department. You got Spanish on either side, Italian down this end, but I really think it's very fitting for our class because of all of the math classes that you're going to take. This one probably has the most heavy language component to it, okay? So I'm going to speak a lot of geometry to you as we move throughout the course of this semester, and it's going to be a lot like a foreign language. I'm going to say certain things, and words that I say to you may have particular meanings in your mind right now, but those meanings will change as I define them in terms of a geometric understanding. Like, for example, I want everybody right now in your mind to picture a line. Go ahead, picture a line in your mind. Okay, you got what it looks like? You can see a line in your mind? All right, good. How many of you pictured a straight path that goes on forever and ever in both directions? No? Because that's actually what a line is. It's a straight path that goes on forever and ever in both directions, right? What, yeah, Jace, question? No? Okay, you can't stretch like this with your hand up because it looks like you got a question, bub, right? Okay, we talked about that. All right, so we're going to define some terms today, and I'm going to speak some geometry to you, okay? But you've got to be able to understand my language when I speak it. You got to be able to understand my language when I write it. You have to be able to write in my language to communicate it to me, okay? And then you need to be able to see certain symbols and understand what those symbols mean in terms of what I want you to do with your math, okay? So there really is a very heavy language component to it. So we're going to start at the very beginning of where Euclid started, and we're just going to look at some foundational words so that I can use them with you as we begin to talk about our first unit of geometry. All right, so we're going to start right here at the beginning with a point. So a point is a location in space. It's a location in space. It's right here. No. It's over there. No, wait, no. It's right there. It's a location in space. Okay. Now it has no size or shape. It is what we would call no dimensional. It has no size or space or shape. It is no dimensional, okay? However, that seems sort of vague if you think about it. It's kind of hard. Well, how do we talk about something specific if it has no size and shape? And so we've established sort of a common way of talking about these things and indicating them. And so, for example, if I wanted you to know about this particular location in space, I would put a little dot there on my paper, and then I would label that little dot with a capital letter. That capital letter indicates one location in space. So when I put that little dot on my paper here and I write a capital C, I'm talking about this location in space right here at point C. However, if I wanted a different location in space, I would put that dot at a different place and I would have to give it a different name. Or put that dot at a different place and give it a different name. But anytime you see a capital letter and that dot, it's referring to a location in space. Okay? That's what we're talking about there. Now you can see some examples that I used here. When we're writing points, we just write the capital letter. We don't need to say point A. When we write the capital letter A, that indicates to us that we're talking about the location in space at A. That's what we mean when we say that. Okay? All right, so let's talk about a line. All right? So a line is made up of points that run together so closely that they make a solid path. Now a line has length, but not width, which makes it one-dimensional. Now you heard me start to use some of this language when we were doing our area and perimeter, right? Perimeter is a one-dimensional measurement, whereas area is a two-dimensional measurement. We'll talk about that in a second, right? Points are no-dimensional. Lines are one-dimensional because we are only measuring their length, not their width, all right? Now, lines extend, as I said, infinitely in both directions, and they can be straight or curved. So we could have an example like this. Draw that and put a little M there and put a little N there. Or we could have an example that looks like this. And I want you to put a little X here and a little Y here. Okay, so lines can be curved and they can be straight. Now, I want you to notice this. Since this class deals mostly with straight lines, that's what we're going to talk about when I talk about lines and the parts of lines that we're going to study. So we're talking about straight paths here. Now, we will talk about some curved lines, okay? The curved lines that we're going to talk about mostly, there's one particular curved line that's equidistant from another point in space. Does anybody know what that curved line is called? It's a curved line that's equidistant from another point in space. A circle, right? So a circle is a line, actually. It's just a curved line, and all the points are equidistant from another point in space. And parts of a circle are called arcs. And so we will look at some curved lines, but mostly we're going to talk about straight lines. So you can just know that as we're kind of moving forward here, okay? All right. So a line can be drawn through any 2 points. And these points I like to call anchor points. They anchor our line in place. And we use those points to name a line. Okay, so you can see I have these 2 points on my curved line up here, and I have these 2 points on my straight line over here. And lines are drawn with arrows on both ends to indicate the infinite length in both directions. So you can see that I've got these 2 points, these lines up here. Now, lines are most commonly named using what we call geometric notation. Geometric notation. Okay? So, for example, I'm going to name this line right here. And so the way I'm going to write it is I'm going to take the 2 anchor points that it passes through. I'm going to write the 2 capital letters. Those are the points. And then I'm going to put this symbol up above it, a straight path that's got 2 arrows on either side of it. This is read line XY. It is the straight path that extends infinitely in both directions through point X and point Y. That's how you're to understand that. Okay? Now, because lines can be followed in both directions, because they infinitely travel in both directions, you could have it labeled XY like this, or you could call it YX. Those are both acceptable. Okay? Sometimes, and this is sort of more of an old school way, lines can be named with a lowercase cursive letter. And so if you see that, it's going to look like this. Watch. We'll put a little T up here outside the line. Okay?
Attention all campus ministry students. If you are coming back from the retreat, please wait for your bus on the memorial side of campus. You cannot wait on Holy Cross side of the campus. Once again, all campus ministry students, if you are coming back from the retreat, please wait for your bus on the memorial side of our campus. Once again, you are not allowed on Holy Cross side of the campus. Thank you.
Once again, let's have that one more time. Can we get that announcement once again? Okay, all right, here we go. Woo! All right, so sometimes you're going to see a line named with a lowercase letter. Watch this. Shh, let's refocus. All right, in that case, this line could also be called line T. All right, so now the question becomes, how do I know whether this is line T, line X, or line Y? Well, line T is a lowercase cursive letter without a point. You see that? There's no dot there. So that means it's naming to the line. Whereas this is clearly capital letter X, that's point X. These two would need to be included in the point naming of the line. Now, this is going to be the most common way you see it. This is kind of an old school way, but you're going to see it, so you need to know what it is. All right? Okay. Any questions so far? Everybody good? Right? You got the points. You got the straight path that stretches between them. Lines extend infinitely. That's what the arrows are for. All right, good. Now, this is where it gets a little tricky. Points on the same line are called collinear points. Collinear points. It literally means with line. I have people that I go to work with They are called my co-workers. And this is points that sit on the same line. They are collinear points. All right, so here's what I want you to do. I want you to draw a pathway that looks like this. We're going to put a couple arrows on that. And then right about here, we're going to put a C. And then right about here, we're going to put a D. Okay. And then I want you to do another path going like this. I'm going to extend it in both directions. So we'll put a little arrow there, a little arrow there, and then right here, we're going to put an E. Okay. Okay, ready? Question. Are points C and D collinear? If you think yes, show me a 1. If you think no, show me a 2. Are points C and D collinear? Yes or no? Yes or no? C and D. Are C and D with one line? Yeah, so that would make them collinear because they sit on one line. Okay, are points C and E collinear? Show me a 1 for yes, a 2 for no. 1 for yes, 2 for no. 1, yes. C and E are collinear. Okay, how about points D and E? Are points D and E collinear? 1 for yes, 2 for no. It's 1 for yes because a line can be drawn through any 2 points. It doesn't show in the picture, but they are collinear. Oh, you see that? Okay, all right, little trick question for you. Now, I got another question for you. And we're talking about straight paths only, right? Because that's what we said we were talking about this class. Are points C, D, and E collinear? 1 for yes, 2 for no. C, D, and E. 1 for yes, 2 for no. Can you draw one straight path through points C, D, and E? No, you cannot, right? Because the only way to draw one straight path is either through C and D, through C and E. If you wanted to draw through C, D, and E, you'd have to turn like that. It's not straight. Or you'd need a curved line, but we said we're not talking about curved lines. We said we're talking about straight lines, right? And so in that case, points that don't sit on one straight path are called non-collinear points. Now, this is important for us. These are points that cannot be connected with one straight path. Any 2 points can be connected with one straight path. So, stands to reason to have non-collinear points, we'd need at least 3. You see how that works? There's got to be a third point. Now, if I had a third point right here, that could still be 3 collinear points. So it has to be 3 points where one of them does not sit on the same line as the other. If we're talking about this line, D is non-collinear. If we're talking about this line, E is non-collinear. If we're talking about this line, C is non-collinear. Does that make sense? See what I'm saying? Okay, now, that's going to lead us into another section in just a little bit. But let's keep going. Okay, now, when I said to you, picture a line in your mind, and I said, did you picture a line that goes in both directions forever and ever, right? What did you picture? Did you picture just kind of a straight path that began and end, right? So you didn't actually picture a line. What you pictured was a segment, right? That's what we call this right here. It's, official name, its formal name is a line segment, but we refer to it as a segment. That's how we differentiate between something that extends infinitely in both directions and one that has a beginning and an end point. So a line segment is a part of a line that has 2 clearly defined endpoints. Okay? That has 2 clearly defined endpoints. Now, question. Let's go back here for just a second. I want you to tell your neighbor how long you think this line is right here. Tell your neighbor, how long do you think that line is? How long do you think that line is? Yeah, it's infinite, right? I heard it a number of times, right? In fact, we cannot measure that, because it is infinite. There's no way we can put a number on that. However, with segments, because segments have definitive endpoints, their lengths can be measured. Okay, well, let's draw an example of a segment. So we're going to draw a straight path here, but this time we're going to put a point A at one end and a point B at the other end, and we're going to cap it off. It's like taking a line that extends infinitely in both directions and then going and chopping the 2 ends off. And now we've got a clear beginning and a clear ending, whichever way you look at it, and that we can measure. And then we can put numbers to it, and then we can do things with those numbers, okay? And so segments are very important for us. Now, just like lines, it's a straight path, so we can have 2 points. We need 2 points to draw any segment. Now, here's how we name segments. We name them differently than lines. We still need the 2 points, so we would still call this AB. But this time, we put this notation above it. Just a straight pathway. No dots at the end, no arrows at the end, but that right there indicates that this is a segment versus a line. See the difference? So when you're writing and you want to say to me in geometric notation, segment AB, you need to write it with that line above it. Okay? All right, now, just like with lines, segments can be listed in either direction. So this could be called segment AB, or it could be called segment BA. Either one is fine. Okay, good. Let's talk about the one that students kind of get a little confused with, array. What is array? Well, array is also part of a line. It has one clearly defined endpoint and another anchor point. Okay, so let's draw a picture of what that might look like here. So let's start with a straight path like this one here. And let's give it one clearly defined endpoint. We'll put a point here and we'll call that R. So now we need an anchor point, which means it's a point that it passes through. So I'm going to put another point down here. We're going to call that Q. Okay. And rays extend infinitely in one direction. So they have a very clear beginning, but then they go on forever and ever. So like I said, with a line, goes on forever and ever, right? A segment, we chop off both ends, we got a beginning and an end. With a ray, we only chop off one end, the other end goes on forever and ever and ever. You got it? That's the difference. It's part of a line. Okay, rays can only be followed in one direction, and it starts at the end point and then travels through the anchor point on infinitely. Now this is the one that's important. When we're naming a ray, there's a very specific way that we have to do that. We have to make sure that the end point is listed first, and then the anchor point is listed second. Now the way that we name arrays, we use a directional arrow above the letters, always pointing to the right. So this diagram right here, if we were going to name that diagram, the way we would write it is RQ, directional arrow to the right. This is red, ray, RQ, okay? Now, let's be very clear about something. This cannot be written ray, QR. That is a no-no. Because the end point must be listed first, and then it travels through the directional arrow. Now, one other thing I want you to see. This is not written like that. That is also a no-no. Because no matter what direction our diagram of our ray is pointing, I intentionally drew this one down and to the left. It could go up and to the right, or it could go this way. No matter what direction it's pointing, when we write it, we always write it like this. So just like we read from the left to the right, we're going to read our ray from the left to the right. So we're going to start here and move this direction. And so it's R comes first, Q. This arrow always points to the right. You guys got that? That's super important when you write your ray language. Okay? Lines, infinitely in both directions. Segments, beginning and ending, part of a line. Rays, one goes forever, and you have a clear beginning point. Okay? 3 different types of straight paths we're going to deal with in this class. All right, let's talk about a plane. A plane is a flat surface, and this is made up of points. So flat surface has got all these points on it, okay? Planes have both length, Kyler, you're going to want to sit up nice and tall, and width. They are two-dimensional. They have length and width. Much like triangles have a length and a width and a height and a base, or parallelograms, or even some circles, right? Okay, or at least the space inside the circle. Okay, so I want you to draw this picture here. So we'll use sort of a parallelogram for our plane. Planes extend infinitely in both directions, like lines. So what we're going to do is we're just going to do some arrows like this to indicate that a plane would extend infinitely in two directions. Now, of course, probably the closest example to a plane I can give you is like a piece of paper like this. Obviously, this doesn't extend infinitely in both directions, but that would be the idea of a plane. And we could have planes that do not touch each other and they sit and they float above each other like this, or sideways like that. But we could have planes that intersect as well, okay? And so we're going to be talking about that as we continue and move forward a bit. All right, so let's go on and continue defining out our planes a bit more. All right. Now, planes are named with a minimum of 3, watch this, non-collinear points, okay? Sometimes planes will be named with an upper cursive letter. Again, that's sort of an old school way of doing things, but they're named with 3 non-collinear points. All right, let's do this. This will kind of help us understand this. Let's again draw another parallelogram looking shape here. Okay, and we're going to put a point here, X, and we're going to put a point up here, and we're going to call that Z, and then we're going to put a point over here, and we're going to call that Y. All right, now I want you to think about this in terms of containing these points X, Z, and Y. If I wanted to contain points X and Z, I wouldn't need a plane. I could do that with a line. If I wanted to contain points Z and Y, I wouldn't need a plane. I could do that with a line. If I wanted to contain points X and Y, I wouldn't need that plane. I would do it with a line. That's the least, most restrictive thing that I could do. However, the only way that I can contain 3 non-collinear points is by wrapping them in this 2-dimensional shape. Do you see how I did that? Okay, that's the only way that I can contain those 3 points. Now, these 3 points all sit within the boundaries of this 2-dimensional shape. I'm able to put them together. Now, that gives us the lead to how we name these. So when we name these, we write the word plane, and then we use the 3 non-collinear points to name them. So this plane would be called plane XYZ, or XZY, or ZYX, or YZX. Doesn't matter what order we put them in. It's the 2-dimensional surface that contains 3 non-collinear points. Does that make sense? Pretty okay there? Okay. Now, like I said, there's an old school way of seeing this. Sometimes they use like uppercase cursive letters, and I know you guys don't really do cursive anymore, but you might see this in the upper right-hand corner of a plane, and in that case, we could say that this is named plane, and then we do like this sort of upper cursive letter. Again, that's sort of more of an old school way, but you're going to see it, so you need to know what it is. All right. Again, just like line T on the front, you'll notice that this does not have a point on it, and you'll notice that it's not a typical non-cursive capital letter, so therefore, this is not a point on there. Like we wouldn't say, oh, I could make line point ZM, line ZM like that. That's not a point. I can't do that. Okay, does that make sense? See how that works? All right. Now, points that sit on the same plane, like X, Y, and Z, are called coplanar. Well, that would make sense. They sit on the same flat surface. Collinear points sit on the same line. Coplanar points sit on the same flat surface. Points that don't sit on the same flat surface are non-coplanar points. Non-coplanar? Wait, how do I get a not on the same flat? Here, let's do this. Draw with me. Make that. Got it? Do this. Do this. Do this. Do this. All right. Put a little point X, put a little point Z, put a little point Y. That is our plane X, Z, Y from over here. You see it? Okay. Watch this. Out here, put a W. That is a non-coplanar point with X, Z, Y. See it? Because it doesn't sit on the same flat two-dimensional surface as X, Z, Y. So then how many points would we need to have non-coplanar points? We'd need a minimum of 4, huh? Okay, good. All right, so non-coplanar points are going to be 4 points that don't sit on the same flat two-dimensional surface, and that leads us into 3-dimensional geometry, which is the first unit that we're going to be studying. Okay? So as we talk about 3-dimensional geometry, you're going to see a lot of non-coplanar points. And so this is language that I'll be able to use with you now as we begin to talk about our geometry. All right, a couple other things just to make clear vocabulary-wise. 2 lines always intersect at a point. We knew that from Algebra 1, systems of equations. The solution is always the point where the 2 lines cross. And 2 planes are always going to intersect at a line or segment or ray, some form of a straight path, right? Again, the 2 pieces of paper here sitting on top of each other on their edges. So when we take 2 planes and we intersect them, they're going to intersect in a straight path. Okay? Big language lesson. Lots of things in here. Writing, speaking, understanding. So as we begin to move forward in our geometry class and I start to use some of this language, this is what you want to be familiar with, okay? All right, let's talk over